Welcome back. This is our last segment in our module on stochastic gradient methods. And we've talked about a few. In particular, we talked about stochastic gradient descent. We talked about stochastic gradient descent for strongly convex functions. And then we also talked about how to reduce variance. We talked about this in two ways. One was using mini-batch, and the other was with an algorithm called stochastic variance reduced gradient descent, or SVRG. And a good way to wrap up this segment is to talk about gradient descent versus SVRG in a context where we can compare both, namely in the context where we have smooth and strongly convex functions. So the setting for this comparison is going to be when we want to minimize a function f that, as always, when we're talking about stochastic gradient descent in the setting where we're motivated by empirical risk minimization, our function f is a sum of many functions. And I've written on the top of this slide 3 algorithms: gradient descent, this is something we covered a long time ago, stochastic gradient descent, and SVRG. And I want to compare all 3 of these in the setting where each fi is beta smooth and the overall function f is alpha strongly convex. So one motivation you can have in mind, a simple example that satisfies these 2 properties, is when f of x is just the loss function for ordinary least squares. And so as an example for you to keep in mind, f of x is equal to 1 over n times ax minus y 2 norm squared when a has n rows. When a has n rows, this is exactly equal to the sum of ai transpose x minus yi squared. So each fi we can see is just ai transpose x minus yi. So we're interested in this setting because this is home court to SVRG, and it's home court to gradient descent in the sense that SVRG, we developed it in the setting where we wanted to exploit smoothness and strong convexity to see if we could boost the sublinear convergence rate of stochastic gradient descent in order to get a linear rate algorithm. And gradient descent, of course, we've seen converges linearly in this setting. So we need to do a fair comparison. And so we're going to compare these 3 algorithms, gradient descent, and actually we're also going to compare gradient descent plus momentum, which is called accelerated gradient descent. Stochastic gradient descent and SVRG. And my comparison here is I want to figure out accuracy versus the number of gradient computations that I have to do. So let's move to this and see what the comparison is. So we need to talk about the cost for one step of each one of these algorithms, again, in terms of gradient computations. And then we're going to just write down our convergence rate for each one, and by multiplying those 2, we'll basically have the trade-off for each one of these algorithms of number of gradient computations in order to achieve a certain accuracy. So let's take them just in the order that I've written them. So the gradient descent algorithm, one iteration of that, tells me that xt plus 1 is equal to xt minus step size times the gradient of my function f at xt. So let me write down again what f is. We're trying to minimize f of x is equal to 1 over n sum of fi of x. And therefore that means that the gradient of f is equal to 1 over n times the sum of the gradient of fi. So that means that one gradient evaluation of the overall full function f requires n gradient evaluations. So one step of gradient descent requires n gradient computations. Again, n is the number of data points in an ERM problem that would lead to this formula format, but just in general, n is the number of component functions fi that I have. What does SGD do? SGD says that xt plus 1 is equal to xt minus eta times the gradient not of the overall function f, but some randomly selected fi of xt. So this requires just one single gradient computation. And finally, we have SVRG. SVRG is a little more complicated. We have to remember what the algorithm is. So recall that SVRG is this two-pass algorithm. And our convergence rate is given in terms of the number of outer passes. So what I'm going to call one step of SVRG is one outer loop, one full outer loop. Now, what did the outer loop require? So recall that SVRG, the outer loop, required one full computation of the gradient, requires a computation of the full gradient, and that means, just like gradient descent, n gradient computations. And then the inner loop is t SGD steps, or t is the number of iterations of that in that inner loop. So each SGD step requires one gradient computation. T SGD steps requires t gradient computations. So total for SVRG is n plus t gradient computations. And if you remember, or if you don't remember, if you look back at the previous lectures to see the specifics of the algorithm, in order to get the guarantees we choose t to be actually a function of some parameters of the function we're seeking to optimize. So we choose t to be some multiple. What exactly the multiple is doesn't really matter. We're not interested in the constants in this analysis, but the actual constant we had chosen for our calculations was 10. Again, that's not significant. Times the condition number, which is equal to the smoothness parameter divided by the strong convexity parameter. So beta f, each fi is beta smooth, and the overall f, not each fi, is alpha strongly convex. So far this doesn't help us so much. So far, one iteration of SGD is by far the least expensive, and SVRG is the most expensive. But in order to make a fair comparison, we need to see how many of these iterations we need in order to get epsilon accuracy. So let's put this all together. So gradient descent has a convergence rate of order beta over alpha times log 1 over epsilon. We need this many iterations of gradient descent in order to get to epsilon accuracy. We need this many iterations for epsilon accuracy. And for accelerated gradient descent, in other words, gradient descent where we also employ momentum, we can improve this using momentum or acceleration to order square root of beta over alpha. Now, since beta is a quadratic upper bound and alpha is the parameter for a quadratic lower bound, beta will always be bigger than alpha. That means beta over alpha is bigger than 1, and therefore we're happy when we take a square root. It makes things smaller. Square root of beta over alpha times log 1 over epsilon, again, iterations for epsilon accuracy. Putting this together with what we wrote on the previous page, which is just namely that one iteration of gradient descent requires n gradient computations, we have that gradient descent needs order n times beta over alpha, or in the best case, square root of beta over alpha, times log 1 over epsilon gradient computations for epsilon accuracy. Beta over alpha or square root of beta over alpha. I just won't write everything. What about SGD? So SGD, as we had said, and really what motivated our efforts to try to control the variance, cannot take advantage of smoothness. It has to take a small step size. However, as we said in a previous lecture, it can take advantage of strong convexity. So for an alpha strongly convex function, stochastic gradient descent needs order 1 over alpha epsilon iterations for epsilon accuracy. So you can see that compared to log 1 over epsilon is much more. However, each gradient computation, each iteration of stochastic gradient descent only needs one gradient computation, so it's actually this same number. So we need order 1 over alpha epsilon gradient computations for epsilon accuracy. Let's just look at this number compared to the gradient descent number. How do these compare? Well, we see that there's no strict dominance here. If you don't care about a particularly small epsilon and your n is very, very big, then gradient descent takes more computations than SGD. So SGD is your better choice. On the other hand, if you're interested in a very small epsilon, then because log 1 over epsilon is so much smaller than 1 over epsilon, then gradient descent is the better choice. SVRG is going to try to combine the best of both worlds in some sense. So SVRG requires order log 1 over epsilon iterations for epsilon accuracy. If you recall, for the specific numbers we chose of step size being 1 over 10 beta and the number of inner iterations being 10 times the condition number, in other words, 10 times beta over alpha, we saw that the convergence was 0.9 to the number of iterations. That was the contraction factor. So its 0.9 is in contrast to something that depends on the condition number. It doesn't depend on the condition number. And that's why you see just log 1 over epsilon here as the number of iterations we need for SVRG, compared to gradient descent where we need beta over alpha times log 1 over epsilon, or in the accelerated case, the square root of that. So both gradient descent and accelerated gradient descent, the worse conditioned your problem is. In other words, the larger your smoothness parameter and the smaller your strong convexity parameter, the more iterations you need for epsilon accuracy. This is not the case for SVRG. So how does that happen? Well, it happens because we're paying a bigger price per iteration. Remember that one loop through SVRG, as we wrote on the previous slide, doesn't take a fixed number of steps. It takes n plus t, where t is the number of iterations, and we're choosing t to be a multiple of beta over alpha. So gradient descent, the cost of one iteration is always fixed regardless of beta and alpha. It's just n gradient computations. But SVRG, the cost of each iteration, the way that we've chosen the parameters, actually grows when beta over alpha grows. So we lose there, but we win here. And in the balance, you see that SVRG comes out ahead. So putting this all together, this means that we need order n plus t. Again, t is some multiple, 10, but because I'm using big O notation, I'm going to just drop that constant. N plus beta over alpha times log 1 over epsilon. So we can see how this compares. With gradient descent, we have beta over alpha times n, with stochastic variance reduced gradient descent, we have beta over alpha plus n gradient computations for epsilon accuracy. So there's not a clear winner in all regimes. So it's important to have all of these and be aware of different trade-offs. So SVRG is particularly attractive for problems that are not very well conditioned, because you don't have to eat this multiplicative factor of beta over alpha times n, or even square root of beta over alpha times n. And there are indeed problems that have very poor conditioning. So just summarizing that, SVRG is appealing when beta over alpha is very large. So when does that happen? This is not atypical in empirical risk minimization problems. When strong convexity comes from a regularizer. I'm not going to go into details about this because this isn't a class on ERM, but I'll just say that it's typical, or let's say not atypical, to see beta to be constant. So let's just call this order 1, and alpha to be quite small. So alpha to be order 1 over root n, or even alpha to be order 1 over n. So if alpha is equal to 1 over n, then this means that beta over alpha, and beta is also is a constant, it's not growing, then beta over alpha is going to be something like order of n. So you can see that SVRG gives you a significant advantage by having the number of gradient computations for epsilon error scale like n plus n rather than n times n. This concludes our discussion on stochastic gradient methods. We'll pick this up next time.